Okay, let's talk about group homomorphisms. Now, there's a reason that we start with sets before anything else when we're getting into higher math. And it's because sets are kind of the prototypical underpin of everything we're doing. Okay, so think about if I have two sets, A and B, and I have a function between them, F. Okay, now we know, what a function is. A function is a rule that takes an element of A and it assigns a unique element in B. And that's what a function does. This is when we're just dealing with sets. Now, when we're dealing with groups, we start with the same basic idea. I have a group G and a group H, and I'm going to have a homomorphism between them that I'm just going to call phi. So the first thing that phi does is it takes an element of G and it assigns to it a unique element in H that I'll call phi of G. Now, at the most basic level, a homomorphism is just a function, but there's extra, right? The same way that a group is a set with something extra. And that extra is just the multiplication on the group that satisfies all the axioms, right? Closure, associativity, inverses, and existence of an identity. So when we're dealing with a homomorphism, this is the general basic idea. So here's my group G again, here's my group H, and here's a homomorphism between them. And this is the intuition behind what a homomorphism does. If I take elements in G, call them G1 multiplied by G2, and say they equal an element G3. So if this is true in G, then when I apply the homomorphism, then phi of G1 multiplied by phi of G2 has to be equal to phi of G3. And this is what we're saying, this is what we mean when we say that homomorphisms satisfy this property, that phi of G1 times G2 is phi of G1 times phi of G2, where over here on the left, inside the parenthesis, this is multiplication in G, and over here on the right, this is multiplication in H. And so that's what I'm getting at when I say this. If G1 times G2 equals G3 in G, then phi of G1 times phi of G2 equals phi of G3 in H. This is the intuition behind what a homomorphism actually does. Now, this idea that when I have G going to H with homomorphism phi, this idea that phi of G1 times G2 is phi of G1 times phi of G2, just with this definition of a homomorphism, we can actually get a lot of the familiar things that homomorphisms do. For example, if I take phi of the identity element in G, well, that's phi of the identity in G times the identity in G, and then apply the homomorphism property. That's phi of the identity in G times phi of the identity in, phi of the identity in G. But now look what we have. We have this is equal to this. And so we do that familiar thing we do in algebra all the time, where we take phi of the identity in G and then multiply by its inverse. And do the same thing to the right-hand side. Phi of the identity in G, phi of the identity in G times phi of the identity in G inverse, right? So these are going to cancel out. These are going to cancel out, and all that's left is going to be the identity in H, because that multiplication is happening in H. So this is going to be equal to phi times the identity in G. And so, you know, we get that property that homomorphisms, homomorphisms map identity to identity. You can play a similar type game and get also that, you know, a homomorphism applied to the inverse of an element is equal to phi of G inverse. So all of those properties come from just the definition of what a homomorphism does. Now, I want to show you two important properties of homomorphisms, or well, two different subgroups that we get just from looking at homomorphisms that end up being super duper important. So let me take my two groups, G and H, and I have my homomorphism between them. I'm going to call it phi. Now, we know that every group has an identity element. So there's E and G, and I'll use green to get the identity in H. Okay. There is a subset of G, actually a subgroup of G, that consists of everything that gets sent to the identity. So everything that gets sent to the identity is what we call the kernel of phi. That's everything that gets mapped to the identity in G. Excuse me, to the identity in H. Now, we can look at a subgroup of H over here that consists of everything in G where it goes. We look at where everything in G goes, and this is called the image of phi. So those are two important subgroups we get. The kernel of phi is a subgroup of G, everything that goes to the identity, and the image of phi is a subgroup of H. And it's everything in G that gets sent to something in H. It's the image of phi. Okay. You know, we can write this out in set builder notation. This is equal to every H in H such that there exists a G in G with phi of G equal to H. And that set builder notation can be hard to parse, which is why I kind of drew that picture. And the kernel is every G in G such that phi of G is equal to the identity in H. And again, thinking about that in terms of that set builder notation can be kind of tricky. So that's why I drew the picture, which is a good picture to kind of have in your head. Let's look at a quick example. So I'm going to take the group of integers, and I'm going to define a homomorphism to the group of integers mod n. And we'll just call this phi because we've been doing that. And here's how I'm going to find the homomorphism. I'm going to send 1 to the element 1 inside this modular group Zn. 1 to the class of 1. Now, it's a theorem that you've probably seen that cyclic groups are completely determined by where the generators go. In other words, any homomorphism from Z into any other group is completely determined by where 1 goes. I'm not going to go into a lot of detail about that other than to say something like this. If I want to see where the element 2 goes, that's just 1 plus 1. And because this is a homomorphism, this is going to be the same thing as phi of 1 plus phi of 1, which is, you know, it's class of 1 plus class of 1, which is just the class of 2, right? And you can play that same kind of game until you see where n minus 1 gets mapped to. That's going to get mapped to, you know, the same thing. That's phi of 1 plus phi of 1 plus phi of 1, where we're adding this n minus 1 additions. And that'll work out to be the class of n minus 1. And then when you see where n goes, well, that's going to be phi of 1 plus dot 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 plus phi of 1. Now it's added n times, or m additions rather, that's going to get mapped to the class of n, which is equal to the class of 0. So, and the reason I wanted to show you this is this gets back to the idea of this intuition behind homomorphisms, that if I have two groups, that G1 times G2 equals G3 implies that phi of G1 times phi of G2 equals phi of G3. In other words, the structure of G is reflected to an extent inside the structure of H. When I say structure, I mean the group structure. The group structure on G is reflected in the group structure of H. And this is going to be relevant when I talk about isomorphisms. So the group structure on the integers is reflected into the group structure of Z mod n up to a certain point, right? Once I get past the integer n, in the integers, things start over again. They start repeating because this is a finite cyclic group. Okay, so keep this in mind, and then I want to show you another example. Or rather, this is more like a non-example. What if I tried to define, suppose I want to define homomorphism Zn into the integers. So again, these are cyclic groups. So let me define the class of 1 to go to some integer that is not 0 in Z. Okay, so I'm going to send the class of 1 to some non-zero integer. Well, what happens if I call it phi again? What happens if I try to do phi of n? Okay. Well, what happens is, this is going to be phi of m plus phi of m, playing that same game we did before, plus phi of m, and this is added up in additions. So I'm going to get n times m. But here's the problem. This is the same thing as phi of the class of 0. And it has to be equal to n times m, but this is not equal to 0. This is not 0 in the integers. So here I have the identity element nz of n mapping to a non-identity element in Z. This is impossible, because remember, homomorphisms map identity elements to identity elements. So what we get from this is, for any Z mod n, there is no homomorphism into the integers, just because of those properties that we've talked about before. Okay, so now we're going to move on to talk a little bit about isomorphisms. Okay, now just like before, we're going to consider sets. Okay, so what would be the analogy with sets that we have considering isomorphisms in groups? And it's just bijections, that's all. So what does it mean for two sets to be bijective? Well, let me have a set A and a set B, and I'm going to define a function between them, f, and f is bijection. That means that it's one-to-one and it's onto. Well, the only way that can happen is the cardinality of A has to be equal to the cardinality of B. In other words, they are essentially the same. Okay, and the same for sets just means cardinality. A and B are the same sets as far as any function can tell. Functions can never distinguish between A and B, because all functions between sets do is they just look at how many elements they have. That's all a function can do. Now, how would that work for groups? Well, an isomorphism. So if G is isomorphic to H, we want to be able to say that G is essentially the same as H. Now, what does essentially the same mean for groups? Remember, a group is just a set with a binary operation that satisfies their axioms. So essentially the same means, well, it would mean that they're essentially the same as sets. They have to have the same cardinality, and the group structures have to be essentially the same. So in other words, if I have G and H, and I'm going to have an isomorphism between them, then G1 times G2 is equal to G3 if and only if phi of G1 times phi of G2 equals phi of G3. Okay? Said another way, H1 times H2 is equal to H3 if and only if phi inverse of H1 times phi inverse of H2 is equal to phi inverse of H3. So the group structures are identical. Remember, I said before in that other picture that I drew that if there's a homomorphism from G to H and the group structure in G, you can find it somehow inside of H. Well, if there's an isomorphism, the group structures are identical. They're just expressed in different ways. That's what an isomorphism means. They're essentially the same. And again, essentially the same for groups means, first of all, they're same. This is in scare quotes because it doesn't mean they're equal. It means they're isomorphic. It means they're the same as sets, which means they have the same cardinality. And the group structures is the same. And the intuition behind what that means is this. That's what I mean by saying the group structures are the same. So they're two sets with the same cardinality, and the group structures look alike on both sets. And that's what an isomorphism is. A formal definition of an isomorphism, well, morally speaking, an isomorphism should be defined this way. Homomorphism phi from G to H is an isomorphism if phi is bijective and phi inverse is a homomorphism from H to phi. Morally speaking, isomorphism is a homomorphism going from left to right and from right to left, and it's bijective. Typically, books will usually say something like this. The definition of an isomorphism is a bijective homomorphism is an isomorphism, because it's pretty easy to prove that if a homomorphism is bijective, then the inverse function is also going to be a homomorphism. Actually, let's look at that, because this is a nice exercise to see how isomorphisms work. So proposition: if phi from G to H is a bijective homomorphism, then the inverse function from H to G is also a homomorphism. Okay, so I'm not gonna go through a full proof, but here's the idea of how that works. So what we want to show is that phi inverse of H1 times H2 is equal to phi inverse of H1 times phi inverse of H2. That's what it means to be a homomorphism. Well, okay, look, because phi is a bijection, it's going to be onto, right? It's going to be onto, which means I can find elements G1 and G2 that are going to map to H1 and H2. So I can write phi inverse of H1 times H2 to be phi inverse of phi of G1 times phi of G2. And remember, all I'm using is the fact that phi is a bijection, therefore it's a surjection. It's onto. Since it's onto, for any element in H, like this guy right here, for any element in H, I can find a G1 that is going to map to it. That's why I can say that's phi of G1. Right? These are the same two elements. Well, now I'm going to use the homomorphism property of phi to say this is equal to phi inverse of phi of G1, G2. Okay. So that means I can cancel out phi inverse and phi as functions because they're inverse functions of each other. So this is going to just be G1 times G2. But remember how G1 and G2 were defined, right? It was defined as G1, phi of G1 is equal to H1. That means just thinking about this as elements of sets, that G1 is equal to phi inverse of H1. So this is equal to phi inverse of H1 times phi inverse of H2, because H2 is defined this way. So I just take the inverse. And so at any rate, I get that phi inverse of H1 times H2 is phi inverse of H1 times phi inverse of H2. So we've shown that if I start out with a bijective homomorphism, then the inverse function is also a homomorphism. Let's do an example. I want to show that the set of real numbers with the operation of addition, so this is a group, is isomorphic to the set of positive real numbers where the operation is multiplication. So ordinary addition on the real numbers. This is my first group. This gives me an abelian group structure. And just looking at positive real numbers with the ordinary multiplication on the real numbers, that also gives me a group structure. I want to show that these two are true. And to show that you have an isomorphism, first of all, you have to define a function between them. You have to show the function is bijective, and you have to show the function is a homomorphism of groups, okay? And for 2 and 3, it doesn't matter what order you use. You can show it's a homomorphism, then show it's bijective, or show that it's bijective and then show it's a homomorphism. But this is how you show that there is an isomorphism between two different groups, okay? So what function do I use here? I'm going to define a function f from the real numbers to the positive real numbers by saying that f of x is going to be equal to e to the x. Just exponentiation. That's all I have to do. So why is this bijective? Well, I mean, you know, just think about what the graph of this looks like. What the graph of the exponential function looks like. So this is 1. It's just, you know, it comes through here, then it rises and it crosses right here and it keeps going up. Well, it passes the horizontal line test, right? It passes the horizontal line test. So it's 1 to 1. And every positive real number is going to get hit by this function, right? any positive real number that I pick, whoops, along the y-axis up here, this function hits it, so it's on to. So this function is 1-to-1. So this one is checked off. It's 1-to-1 because it passes the horizontal line test. The graph of it does. It's on to because just looking at the graph, anything that's a positive real number, this function takes on that value. So it's 1-to-1 and on to. So it's a bijection, and then showing it's a homomorphism. Well, to show 3, we have to show that f of, I'll say x1 plus x2 has to be equal to f of x1 times f of x2. Now, I picked this example on purpose because these two different groups have two different operations on them. The group of real numbers has an addition operation on it. And the group, the way that the group that I picked, and this second group has a multiplication operation. So when I check the homomorphism, I have to respect the operations. So over here in the right, I have an addition operation. Oops, let me not use circle plus. It looks like something different. I have an addition because this is an addition inside this group right here. But over here on the right-hand side, this is a multiplication because it's multiplication inside this group. The operation is multiplication. Well, let's see what happens. F of x1 plus x2, that is e to x1 plus x2, because that's what my function does. It just raises something to a power. Okay, but we know how exponents work. This is the same thing as e to the x1 times e to the x2, but e to the x1, that's applying my function to x1. E to the x2 is applying my function to x2. That's exactly what we wanted. So that means we've shown that this function, so I have r to r plus, and f is my function, is an isomorphism because it's a function that is bijective, and I've shown that it's a homomorphism, therefore it's also an isomorphism. So a nice little thing to think about is, what is the inverse, right? What is the inverse isomorphism? So, question, what's the inverse? In other words, what function is going to take me from the positive integers, the positive real numbers to the real numbers, and it's going to undo raising, or undo, this e to the x. Well, I got to take an x in here, and it's going to get math. So we're going to call it f inverse, right? So f inverse of x, what is that going to be, right? What undoes exponentiation, or raising, taking x to e to the x? What undoes that? And I'm going to leave that something for you to think about. It's really straightforward. Think about college algebra, and how you undo e to the x. And I think it'll kind of fall out, and then verify that it's actually the inverse. And actually verify that it's a homomorphism, right? And you'll use properties. Well, it's a log, right? You already thought that it's a log. Use log properties to show this is actually going to be a homomorphism. Okay, now getting into your specific questions. You said when you have to prove something's an isomorphism, the part where you have to show the isomorphism is operation preserving. I'm assuming you mean showing that, wait, let me go back. When you have, G to H and some defined homomorphism, and you want to show it's an isomorphism, when you show it's order preserving. When you use a function, how do you know what to use? Does it matter? Well, yeah, it does. But it goes back. But this is also true. You just find one that works. If I just give you two groups, and I say, show that these two groups are isomorphic. Well, you have to find a function, define a function between them. You have to show it's bijective, and then you have to show it's a homomorphism, or what you called up here, operation preserving. Okay. But yeah, you just find one that works, right? If it's not given to you, you just have to find one that works. And it can be tricky sometimes, but you just kind of have to play around with it. I think this might answer your question, and hopefully some of the examples that I did in this clears things up a little bit. But please email me back and let me know if you need more examples, or if this didn't, go into what you were thinking about. And if there's anything out of any of these chapters that you want me to revisit, just say so. And I'm happy to talk with you over it, or make another short little video like this, or, whatever you need. So I hope this helps, and I will talk to you later.